Thank you, Timo. Yes, so now we need to deal with a bit of a tough aspect of MIP solving. Yeah, it can be sometimes very annoying if you encounter numerical troubles when you actually use MIP solvers with large and complex problems. So yeah, we say mixed integer programming. So for instance, if you model a binary variable, you would like to get a value of 0 or 1 back. But then if you actually solve a model, what you might see is the following. That is some SCIP output, and this doesn't look very integer, right? So that's a bit larger than 1. Here it's a bit smaller than 1. Of course, it's very close, but still this is something you might not expect if you naively just start using a MIP solver. Or the following. You look at the log and at some point you become a bit scared because it says numerical troubles in LP unresolved. Unresolved. So what do I do with the result of my MIP solver? Yeah, I can assure you SCIP can handle this, right? If it continues, then it has not made any wrong decisions from that. But of course, it's also not good for performance if something like this happens. Or after you've solved, yeah? SCIP tells you problem is solved, optimal solution found after 2,800 seconds, and then the left-hand side of some constraint is violated. So the solution that you get in the original problem is not even feasible. Yeah. So in this talk, I just want to show you a bit where this comes from, where this might come from, to understand what actually a MIP solver understands by a feasible and optimal solution, and maybe also a bit what you can do about it if you encounter these things. In the second part, I want to go a bit into how you can actually try to really solve linear programs and MIPs exactly. So some algorithms that might give you solutions that are really have no violation at all, and where you can even prove that the result is optimal. Okay. So first of all, yeah, where did these inaccuracies come from? Well, the reason is, as you will know, is that virtually all MIP solvers are built on floating point arithmetic. So here is a picture of double precision floating point arithmetic according to the IEEE standard 754. So this represents real numbers in the following format. You have 1 bit 0 or 1 for the sign of the number. Then you have a large red part, which kind of encodes the mantissa, it's also called, the fraction here. And then you have these 11 green bits, which tell you how large the number can get. So it's the exponent. And so all in all, you get floating point numbers represented like this. So for instance, if you have now an integer that goes up to 2 to the 52, then actually these integers you can represent exactly with these red bits. And so you will not have any error because you can choose the exponent as exactly 1023. And then you have here your integer, well, roughly represented, right? There's this 1 dot, so some technical details, but you can represent it exactly here. And then the exponent part here is times 1. Okay, but as soon as you have integers or numbers that are larger than 2 to the 52, you will not be able to represent everything down to the point. Yeah? And at the same time, you see that this is one advantage of floating point arithmetic, that by having this exponent here, you can represent much larger numbers than you would be able to represent with a 64-bit integer, right? So this is why we use floating point, because, well, it increases the scale of the numbers that, the range of the numbers that we can represent, both towards infinity, but as well towards 0. But of course, it comes with these problems that not every number can be represented and that we have round-off errors. So we can represent around 15 digits with these 52 bits here. And so, well, if you want to represent 1/3, then you will get an error roughly here, right? And this is not only a problem when you try to represent numbers, but of course also when you try to compute with numbers, because the result of the computation will be rounded to the next floating point representable number. And so we can have some look at some examples here. For instance, here in exact arithmetic, 3 million divided by 3 or times 1/3 minus 1 million should be 0, but in floating point arithmetic, you might get something like this. And you see that this error grows if these numbers here grow. So if you add another 6 zeros, of course, in exact arithmetic, it would again be 0, but in floating point arithmetic, it's actually really a large numerical error that you have from this computation. And so you need to be very careful, and developers of optimization software are usually very careful when implementing such operations. But essentially, this is where potential numerical issues come from. Okay, and so now if so maybe just to say this again explicitly, why do we use floating point arithmetic? Because it's, of course, very fast, because it's implemented in hardware, opposed to exact arithmetic, for instance, over rational numbers, which is only implemented in software, and so much, much slower. And so MIP solvers use this floating point arithmetic, and in order to deal with the round-off errors that you have, you need to relax your definition of feasibility from exact feasibility to, well, some tolerance. And so there are different tolerances that MIP solvers use. So the first obvious one is an integrality tolerance. So you say that number alpha is integral if it's within plus or minus some epsilon of integrality. And these tolerances here are usually set to something in the range of 10 to the minus 6 to 10 to the minus 9. Often 10 to the minus 6 is the default tolerance that you find in many solvers. But you can decrease it up to a certain extent. Okay, but then what about constraints? So linear inequalities. So you need to define what it means that A transpose X is less than or equal to B. So one way to do this is to use an absolute tolerance and say, well, A transpose X minus B should be at most some epsilon, say 10 to the minus 6. But you will immediately notice that if the numbers or the values here become very large, so for instance, if the right-hand side is 10 to the 9, 10 to the 10, or like some really large numbers, it may not at all make sense anymore to compare this to an absolute tolerance. So you could also come up with the idea to use something of a relative tolerance, right? I'd only want to be some small factor of the right-hand side larger, 10 to the minus 6. So this would be something like that. So the violation here, normalized by the absolute value of B, should be at most this epsilon. However, this is of course problematic as soon as B becomes very small, right? If B becomes close to 0, equal to 0, then this definition will not be will not work. So, for instance, what SCIP uses is a mixed kind of feasibility tolerance. So if the right-hand side is in absolute value smaller than 1, then we use an absolute tolerance, the first case. But if the right-hand side is larger than 1 in absolute value, then actually we use a relative tolerance. And I don't want to say that this is the better way to go, but this is how it's defined in SCIP. And so I think the majority of solvers, also the commercial solvers, would use absolute tolerance only, right? Express does, I think. No? But of course, this is related to how you scale your model. So you will notice that if you multiply the constraint by a factor, then actually the definition of what absolute feasibility or feasibility in absolute tolerance means changes, right? If you scale this up, then it will be you will have a violation more quickly, right? If you scale this down, then the violation will be scaled down, and then you might say this looks fine. So these tolerances are not invariant under scaling. Well, the relative one is, but I think we agree that that's probably not something you can use in practice, right? But the other two may change if you scale your problem differently. Okay. So now, what can we actually expect if we have such a solution that has such an epsilon violation? So everything is within 10 to the minus 6 of these tolerant of these within the 10 to the minus 6 tolerance in feasibility and in integrality. Then the hope is that such solutions with small residual errors are close to really an exactly optimal solution that doesn't have any violation. So the good case would be this, right? So you get some solution here, this brownish solution in the middle, which has a small violation, and it is very close also to an exactly feasible solution. But that's actually not the mathematically correct interpretation of what a solution with numerically errors is. A solution with numerically errors is actually an exact solution for a perturbed problem. So if you somehow add the error to the problem definition, then your solution is actually feasible. And here you don't really see that this makes a difference, but there are certainly cases where it can. So you see that the violation of this brownish point can be very small. The residual error, we say, so the violation of some constraint can be small, but still the difference to an exactly optimal solution here, if I optimize in this direction and this red error is tilted a bit to the left, can be large. And there are other pictures that you could draw, right? So only having a small residual error does not necessarily guarantee you that you have you're close to an exactly optimal solution. Okay, now then let's think a bit about where these problems can come up. So here's an example. You've already heard the term big M constraints in the modeling session. We have to be very careful when using these big M's. Here's a really very simplified model. You have a variable x, which should be at least 1, and there's an indicator variable, you could say b. If b is 0, then also x should be 0. So actually that can't happen, right? B should be 1. But now if you scale the problem, if you say, oh, I somehow bring this 10 to the 6 to the other side by dividing to have the 1 coefficient in front of this variable b, and you try, then actually x equals 1 and b equals 0 becomes feasible in absolute tolerance. Yeah? If you type in x is 0 here and x is 1 and b is 0, then the violation is exactly 10 to the minus 6. Yeah, this should be non-positive, but it's 10 to the minus 6, but that's fine if our absolute feasibility tolerance is 10 to the minus 6. So the solution x equals 1 and b is 0 is feasible in the scale problem, but infeasible in the original problem. And so, well, this is a very simple case, but this is, in some sense, this could be one of the reasons why SCIP in the log before told you the optimal solution that I computed for you has violations in the original problem. It's actually infeasible for the original problem. Because during pre-solving, SCIP and other solvers, they transform the problem, then they solve this problem, and later you might have, you're solving a slightly different problem, and then when you post-solve and bring it back to the original, you can have violations that are larger than the tolerance. And of course, we're all trying to avoid this, but in some complex problems, this is what can happen. Okay, so what else can we learn from this example? The solution when x is 1 and b is 10 to the minus 6 is actually feasible in both cases, right? Because x is 1, so the first constraint is satisfied exactly, and the second constraint here in the original problem would be 1 less than or equal to 10 to the 6 times 10 to the minus 6 is 1, so also check. And here 10 to the minus 6 times 1 is less than or equal to 10 to the minus 6, also check. Okay, so this would be a good solution in the sense that it's feasible in both problems with respect to tolerances, but in some sense, the b equals 10 to the minus 6. Okay, that is some numerical dirt hanging around there, right? This should be 0. So, and now what happens when you actually fix the variable b to 0 and check? Well, then you realize this problem becomes infeasible. Yeah. So this solution is okay for the feasibility definition of the solver, but it's actually not okay for the application that you may have in mind. So if you want to then implement this, you would interpret the b is 10 to the minus 6 as 0, and then actually you have an infeasible solution for your model, right? So the only reasonable solution here is really the one that we inferred also in the beginning, is x is b and x is 1 and b is 1. Then everything is safe here in the original, and of course as well in the scaled problem. Yeah. Okay. So it's a very simple example to show you that you have to be careful with large coefficients, or let's also say maybe with the ratio between the smallest and the largest coefficient. Yeah. Okay, because we've had nonlinear today, I've had another slide where what can be the source of numerical troubles. So Xenia told you that in MINLP solving, you may use lots of cutting planes or outer approximation cuts or linear inequalities in order to approximate such a nonlinear constraint function. Yeah? And the mean thing here is if you imagine that, for instance, you want to minimize a variable x over this convex quadratic, then actually, and you use some linear outer approximation, then the LP solution will always be maximally far away from this blue line. Yeah? And so you have to cut, and eventually you may get many parallel inequalities, and that will actually then yield problems in your simplex solver. can also yield performance problems because your cutting plane loop does not terminate quickly, but also numerically, if you add a lot of parallel or near parallel cuts, then this creates problems in the linear algebra of the simplex method. Second thing that you've seen in Xenia's talk is that when you relax non-convex constraints, build convex envelopes or linear envelopes of non-convex constraint functions, then the quality and the tightness of this relaxation heavily depends on the bounds. And if you have very large bounds, then also the outer approximations may become very steep. For instance, also in this convex case, you could imagine if you have like no bound out there and you want to build a linear underestimator here at the very left, then this becomes steeper and steeper, right? And then you get kind of linear inequalities which have very large coefficient ratios, like that's exactly the steepness, right? The difference between the largest and the quotient of the largest and the smallest coefficient. So also in MINLP, numerical troubles can come up easily if you use an LP-based branch and bound approach. Okay, so just some examples where problems can come from. Now, what do you do about them? So here is a very dense list of things to consider. And this is maybe also just a slide that one can look through again afterwards, at kind of like a checklist. So obviously, it's good to scale your data to avoid extreme values. So, and extreme values means both in absolute and relative terms. So you want to have ideally all of the coefficients not larger than 10 to the 6. But also the ratio between the largest and smallest coefficient in the rows, but also in the columns, in the variables, you want to have bounded. So also this should not exceed 10 to the power of 6. And essentially, what does it mean to scale data? So you need to look at which units to use for your coefficients. For instance, if you give something if it's a cost and you give it in euro, but you have very, very large costs in thousands and millions, then it's better to use 1,000 euros or million euros as a base unit, right? Or for instance, if you are looking at amounts of some items in a supply chain that are delivered, counting a single screw may not be a good unit, but rather boxes of screws or, I don't know, packages of screws or whatever. Why this is important is because this may also seem very obvious, but as Timo already mentioned, lots of the models that a solver sees don't actually come from manual coding, right? But from some modeling language where you implement an abstract model and then you get some data and the data is instantiated into the model, and then you get MIP that is being solved. And if you build generic optimization solutions for some customers, you may not even know which input data you're getting. So that is why also these things can come up even though they seem obvious to avoid, right? Yes, and then if you have managed to scale the data, or then you should double check whether the definition of this numerical feasibility with respect to tolerance actually makes sense relative to the input data too. So you should think like this inequality, if it's violated by 10 to the minus 6, is that okay for my application, for instance? All right. Two things about small values. So if you have really tiny values that actually don't have a meaning, then consider just setting them to 0. Yeah, as we said, model is always a lie of the reality, but sometimes a lie helps more than the precise reality. But also one has to be careful. So if you represent your data, then just avoid unnecessarily truncating them or losing some precision, because that can also introduce infeasibilities in the model that may not even be there in reality, or it can introduce new solutions that look feasible in your problem but not in your application. So that's just something to take care of. Okay, so this is about the input. So if you want good output, you should try to do your best to give good input. Sometimes, however, it's difficult. Sometimes you simply do not have good bounds on the variables. You do not know what the maximum value of some decision variable will be. Actually, you're trying to find it out in the optimization. And then you have to be more creative in modeling and solving it. So the solvers all have some parameters where you can adjust how they scale the problem or try to scale the problem automatically. So there are different methods that try to automatically do what I told you to do here as a user. If you have a numerically difficult problem, then you can often use some more aggressive scaling techniques that could help. Then we've already seen that big M's can be troublesome, can introduce troubles. And so in the modeling session, I've also mentioned that there are alternative ways to model such if-then conditions, which are not one linear inequality, but rather an implication, an indicator constraint. So which then the solver can handle as it sees fit. It can, for instance, dynamically activate and deactivate the inequality in the branch and boundary, depending on how the indicator variable is set. And then it never has to add such a bad-looking inequality directly. Or maybe it can somehow infer that the big M that it can use is actually smaller than you would think initially, because through pre-solving, the solver has transformed the model, improved the numerics, and that's something that you couldn't even see. So it's really not that this things that I'm mentioning here are just a fallback for what you can do as a user. Often what you try to achieve up here is not possible for the original problem, but maybe possible for the solver after a few steps of reductions. Okay, one further case. So in the real world, often when you talk to practitioners, it will not be clear what the objective function of your problem, of the problem is. Often practitioners have several measures of quality that they all want to optimize. And you need to make a compromise. And then one common thing to do is that you also combine such different objectives into a weighted sum and use this as an objective. And there's one thing that can make things difficult if you combine one objective with a very large coefficient plus another objective with a smaller one, in order to sort of mimic some sort of hierarchy between these two objective functions, right? First of all, optimize number one, but then have number two as a tiebreaker. Okay, and however, this can lead to very large coefficients in the objective function. And this again brings the simplex algorithm, or can bring the simplex method or the LP solver that you use into trouble. And another approach to consider here is to, in this case, to actually split this up into really different optimization problems with different objective functions that you can solve sequentially. So in multi-objective optimization, this is a bit related to what is sometimes called the epsilon constraint method. So what you could, for instance, do is you take your most important objective and you maximize it or you optimize it. Then you know what the optimum is by ignoring all other objective functions. And now you say, okay, I want to be at most 10% worse than this. So my objective, so let's say we maximize, I want to have at least 90% of this value that I saw, 90% of the maximum. And I can add this as a constraint, and then I can do a second optimization of this additionally constrained problem with the second objective, which I want to use as a tiebreaker, and replace 90% by the number that is applicable, of course, in the application. So, and then you can separate these different objectives. And sometimes it's also easier to analyze such an approach combined to when you compared to when you combine all the objectives into one. Yeah. Because that's actually not, well, it's a tiebreaker, but it's not always clear how they are really combined then in the end. Okay. So maybe one last thing. We've talked about poor scaling and imprecise input, and that these can lead to numerical problems, but I want to say they are neither necessary nor sufficient for numerical problems. So if you have numerical problems, they can also come from very well-scaled problems. So there are very nice matrices that have just 0 and 1 coefficients, but if you try to solve a linear system of equations with them, then you get large errors from small residual errors. So we say that they are ill-conditioned. And also in the reverse, it can be that if you have a poorly scaled problem, and then the solver can handle it well. Huh? All right. So these are some general guidelines as a user of a MIP solver, or a user of a MIP solver. Then I have compiled a probably very, very incomplete collection of tools or things that you can do when you run into troubles. So most trivially, all of the solvers have a check of the solution, right? When you've computed it, usually this is even done automatically. Nothing you have even have to do. You just have to look at the log. Yeah. So in SCIP, you get then a statistics on the absolute and relative violation of bounds, integrality, rows, and constraints, because yeah, SCIP has a more general concept that Xenia already mentioned, constrained integer programming, which allows to solve more than just linear inequalities. So this would be to check afterwards just whether it's feasible. But of course, that doesn't tell you whether something went wrong during the solution process. So here is a log output from another open source solver, HISE. You've heard the talk of Julian on Tuesday. So when you input a not well scaled, an ill-scaled problem, HISE may warn you. It tells you the coefficient ranges, and here you already see, well, that doesn't look good, right? You have the smallest matrix coefficient is 10 to the -9, the largest one 10 to the +7. Also the bounds, it says, are excessively large. So consider scaling the bounds and right-hand side down, or setting some other options. Yeah. So this is what can be analyzed already before the solution process starts. But also during the solution process, the log can be very informative. So this is a sample log that you could get from Gurobi, for instance, where it tells you that I've increased some tolerances or tightened some tolerances here for LP solving. Oh, I'm switching to quad precision, trouble encountered, restart. And then it actually tells you that it's having trouble. And something else. And where does this come from? So a lot of the troubles come from solving the LP relaxation. And so we should talk a bit about that. So there's a concept called condition numbers. It's a very general concept in numerical optimization about the problem, essentially how input and output relate to each other. And more specifically, if you have a quadratic matrix, for instance, the basis matrix of a linear programming solution, then the condition number, kappa, gives you a bound on how an error in the right-hand side can propagate to the actual solution value and the values in the solution vector. So I emphasized bounds here because this condition number is often a worst case estimate. Just because the condition number is high, that doesn't prove that you need to have a large error also in the solution vector. But if the condition number is small, then you can be a bit relieved because that gives you really a theoretical guarantee on how errors in the right-hand side, and errors in the right-hand side essentially here means roundoff errors that happen during computation. So it's nothing that you have actually made in your input data, but that's something that the LP solver will just produce by computing with floating point arithmetic. So for the simplex method, you can simply analyze this condition number. A large condition number of a basis matrices indicates that there are larger errors possible in the LP solution. Again, it may all be fine, but you should be careful. Then this is for a simplex solution. What do we do for MIP? So for MIP, when we apply branch and bound, then we solve many, many LPs. And so there's not one simple condition number that we can transfer. There's not one simple basis that we have to look at. But what we can do is that we can compute or sample something like a weighted average of the condition numbers of the LPs that we encountered during the solve. Yeah? And this is implemented in many solvers. So sometimes it's called MIP kappa or attention level, or I don't know which other words are around. Here's an output. It's a screenshot from a slide that I got from Timo, where he presents the output of Express for an instance class 4 from the mixed integer programming benchmarking library with two different scaling options in Express. And each time you can look at, yes, how many of the bases were terrible singular. That means that they could not even be inverted. And then how many were numerically totally stable, suspicious, unstable, ill-posed, so different degrees of troublesomeness, and then they average this and give you some single number which tells you how much attention you would need to pay to the numerics of this problem. So if that attention level here in Express is high, that means you should be a bit wary of the solution that you received. And you also see that if you apply a more aggressive scaling, then actually this attention level decreases here, and the number of bases that are difficult, that are numerically troublesome, are significantly reduced. All right, so this is about condition numbers. Then some solvers also have an analyzing tool. I think Express also has one, but Gurobi also has this model analyzer, and that also comes with an ill conditioning explainer, for instance, which tries to, if I understand that correctly, see are there any rows or columns in your matrix, in your input data, which are very almost parallel. Yeah, and that you can use to actually analyze which part of your problem might need better scaling or maybe reformulation or something else. Okay, things like this exist. Oh yeah, Express has something else, a solution refiner. So once you obtain a solution, well, you're not necessarily stuck with it, right? You can try to actually improve the numerics, the feasibility of this solution. So, and I mean, that's implemented by Express, but that's mathematically a very general concept, right? You can try to reduce or remove violations that you have in primal feasibility, dual feasibility, or integrality. For all the incumbent solutions that you encounter, incumbent solution is always the best known solution that you have during the solution process. So if you find a new one, you can apply something like this, or also just for at the very end for the final solution. And what could you do? Many different things. For instance, you could, if it's an LP solution, you could perform extra simplex iterations to become more feasible, not stop at the first basis where your tolerances are satisfied, but go a bit further, right? Or you could recompute the solution in higher precision. So quad precision would use 128 bits and is of course notably slower than double precision. But if you only do it for solutions and not for the whole branch and bound process, then probably that doesn't hurt too much. And you could also try to push integer variables that have a fractional value out of the basis. So whenever an integer variable has a fractional value, that means it cannot be at its bound, so it must be part of the basis. And you can try to pivot to a different basis, a different representation of the solution where this integer variable then is forced and fixed to the bound, which is of course integer then. Or you could also, during the branch and bound process, do additional branches to force integer variables to integer values. So if you realize that you have such a 10 to the minus 6 for some binary variable in a big M constraint, then you can just do open two branches, right? 0 and 1, and solve it exactly each time. Yeah, and you can also check just by rounding the values of the integer variables to really integers, fixing and see what the remaining LP gives, right? Can I confirm that this is actually feasible? And so here you see that this can increase or improve the properties of such a solution significantly. Simple thing to do, can be very useful in practice. Here I have another tool that's, well, not only focused on numerics, but that we've developed just recently, and so I wanted to mention it. So in the SCIP development, of course, also we encounter regular bugs that are reported by users, that are encountered by ourselves. Debugging can sometimes be a pain, especially when the bugs are produced by very large models. And these models take long to run until actually the error occurs. And so one technique that is heavily used for long in SAT and SMT community and pseudo-Boolean solving, so more in the computer science side of things, is delta debugging. So this is an iterative approach where you try to simplify your model, a bit like in pre-solving, but heuristically. You're not trying to actually transform it exactly equivalently, but you're just trying to reduce the size, fix variables, remove constraints in order to make it smaller, and then try to test whether the unwanted behavior that you have still occurs. Yeah? And so you iteratively try to reduce the size of your problem until you have a very small problem that exhibits the same unwanted behavior that you had in the big one, and then it's much easier to debug on this small problem than on the big one. That's the general motivation. And Alexander Höhn, who is Alex here? Yeah. He's been leading, together with Dominik Kamp from Bayreuth, this development, and that's been super useful also in the development process of SCIP. Yeah, that's an open source package where you can interface different MIP solvers in order to automatically do this delta debugging. And of course, I'm mentioning this here because this can also be used when you have a numerical bug or some unwanted behavior. Yeah? That is due to numerics. Okay, so this about basically how to deal with floating point MIP solvers. And now I want to transition a bit for the last part of the talk into how you can solve LPs and MIPs exactly. That is, I want a solution that has 0 violations and that is also exactly optimal. So I've not lost any potentially better solutions. And for linear programming, I want to start with, well, first of all, reminding you of the essentials here of the basic solutions that come out of a simplex solver. So you remember this slide from the first day. A basic solution has such a m by m square submatrix of your constraint matrix, and then you set the rest of the variables to 0 or to their bounds, and you compute the value of the basic values by, well, here it says B inverse times B, but actually what you do in practice is, of course, solve a linear system of equations. So B times X equals B, or similar for the dual, and you use this using a factorization of the basis matrix B into two triangular factors or some permutation of triangular factors L and U. And so, yeah, if you do this in floating point arithmetic, then afterwards the error will, so the difference, the residual error, the difference between right-hand side and B times the solution will not be 0. No? So there's a very traditional algorithm, a very classic algorithm, how to improve upon this. So this is called iterative refinement, goes back to Wilkinson in the 60s. So, well, so let's solve, let's suppose we want to solve a system B, X equals B. So let's drop this subscript here. And well, I just noticed that on these slides, I did not replace my A's with capital B's everywhere consistently. So the capital A's here should also be a capital B. Yeah, that's my coefficient matrix. So what is the idea of iterative refinement? Many of you may have seen this. So I have my system. I can use floating point arithmetic to compute some solution. Let's call it xk. Then I can compute the residual error b minus a times xk. So I just plug the solution in and compute. What is the error? This should have entries around, well, 10 to the, depending on the condition number of the basis matrix. Yeah, this should be small, hopefully. But if it's not as small as you wish, then what you can do is that you can use this vector of residual errors and put it onto the right-hand side, ax equals b hat, and solve this system again. So this is just a slight modification from this year. And please, yeah, A and B here means the same thing. So, and then you get a new solution, which is a kind of a corrector solution. So if you add this x hat here to your initial solution, then the violation will decrease. So this is a loop that you can iterate. And the trick here is that the solution of these linear systems here on the very left side and here on the very right side, you can do in your base precision like double precision. And then the part where you compute the residual error and where you perform the correction, you can do in a higher precision. So this is a hybrid precision method. And the key is here that, well, solving linear systems or equations is in some sense more expensive. So for this, we use double precision, which is very fast. And here for the things where we use high precision, we actually don't have such expensive operations to do. So we just have a matrix vector multiplication. That's much simpler than solving a linear system of equations. And so in some sense, you do the difficult thing in fast arithmetic and the more simple computations in slower extended precision arithmetic. Even you could even use exact arithmetic, but that may be too slow for some. Okay. And so now what you can do is that you can take this as a blueprint for also refining solutions to linear programs. So this is something that is used in solvers during a normal simplex run. So if during a normal simplex algorithm, you are solving a basis system and you realize I'm not getting the precision I need, then you could simply apply this iterative refinement here, for instance, with double precision and quad precision or whatever. But this would always just be a one-step intervention into some part of the simplex method. Is it not 12:50? Oh. I'm sorry. I really thought that I have to 12:15. Okay, but then I will be very quick. So two things. This thing you can extend to linear programs in the same way and solve basically linear programs exactly. And the nice thing here is that this development that we've had in the Soplex project, in the open source solver Soplex, actually also has made it to industry, to the FICO solver. They've not implemented it with rational arithmetic, but with quad precision in the refinement stage. But for that, you can read more in Timo's blog post here. And the second thing I wanted to tell you that this solution of LPs exactly, you can also use then in a branch and bound process for solving MIPs exactly, which uses exact LP solving, but also much more sophisticated techniques that do not require exact LP solving. And we have also included a lot of the techniques in that you've heard from Timo yesterday and made them kind of exact. And so this is also available on the SCIP repo on GitHub. So it's a version that we will hopefully merge soon. And then SCIP will out of the box have an option where you can solve it to zero violation. Of course, solution will be slower. We are measuring currently roughly a factor of 4, but I think for some problems and applications where this is important, this can be super useful. Thank you very much.